Okay, so remember from last class that we talked about the main idea of sampling distributions. And the notion is that we can get bell-shaped distributions, bell-shaped pictures when looking at the balance of our data that are especially nice whenever we look at the summary, the p-hat, or the summary, the x-bar, for some given sample, some group of information that we've collected. And the notion behind the central limit theorem is, in theory, if you did this a bunch of times, you would end up getting a distribution with these attributes, okay? So we said for p-hat, this was part 1 of chapter 17, that p-hat would be normally distributed, where whenever you were asked what the mean is, the mean would be that p, where p, remember, is the population truth, the population percent or parameter for what is known. And then for the standard deviation, we have the square root of p times q over n. Remembering that q is equal to, let me make a little note here, note p is equal to 1 subtract, or q, well this is the opposites, or you could say q is equal to 1 subtract p. That's the one that you would more likely use to calculate, since typically you will have some idea regarding what the population truth is assumed to be. Now, remember, I'm going to say recall, z-scores. Remember the traditional z-score where z is equal to x subtract mu over standard deviation. And then notice here the pattern where x will still stand for some data value, mu is going to be the mean, and of course sigma stands for the population truth, that standard deviation. So what I'm saying is, for the distribution of p-hat, if you decide to normalize, you do not need to normalize. You can use the normal calculator, you can use the Excel spreadsheet with the original numbers, as long as you have updated the standard deviation by dividing it, right, by n and then square rooting it. But if you would like to normalize first and then use technology, what you would do is you would take your value, x, of course here actually the value that we're approximating is p-hat, so I'm going to put p-hat here, right? Subtract, we said the mean, which is p, over the standard deviation, which is square root of p times q over n. Also from last night, remember that we extended this idea, and we said it's not just p-hat that the central limit theorem covers. In fact, more popularly, the one that I started off with was the idea that we can talk about the shape of lots and lots of x-bars, sample means, being graphed, and what those graphs would look like when my sample size is large enough, or given that we already had something that was normally distributed. So x-bar is approximated by a normal distribution, where the mean will still be whatever that known average, that mu, was. And the standard deviation will be sigma over the square root of n. So again, you have to modify your standard deviation. If you like to find z-scores, the z here, again following the pattern that we just had, where x is the value, the x-bar, and then mu is the mean, sigma was the standard deviation. Following that pattern, we would get that the z-score would be x-bar, whatever the value is you're plugging in or looking at, subtract the mean, which is still the same mu you knew, but now you're going to modify the standard deviation by taking whatever you knew to be the truth and dividing it by the square root of the sample size. And we said last time these are some pretty powerful characteristics, because essentially what dividing those standard deviations by n and then square rooting does is it makes your distributions more narrow. It makes things more consistent, so it gives you more power, either turning things that are not normally distributed into bell-shaped when n is large enough, or taking things that are already normally distributed and making them better, making them more consistent. Now, last time, remember with p-hat, we talked about the conditions, things like randomization, 10% rule, success, failure, the n times p, n times q needing to be greater than or equal to 10. This time, we're going to continue the talk around x-bar and what the conditions are when looking at the sampling distribution for the mean, or the sampling distribution of x-bar. So conditions. And these conditions are to check if n is large enough and to make sure that we can represent x bar like we just discussed, right? So conditions for if my sample size n is large enough and the sampled values are independent. Okay. First condition remains the same. We have randomization. And this randomization, again, can come from something that has been sampled with a simple random sampling technique, or simply knowing that the sample is representative. So we check this first. Second condition is the same also as it was last time, where we have this 10% rule. We need to have less than 10% of the population sampled. And then the third condition is that we have a large enough sample. So typically, if the shape of the sampling distribution already looks normal, you can get a sample of any size. But typically you need at least a 30 or maybe something larger. So this is the rule of thumb we use, and we will get more specific later, okay? The first thing is if this looks normal already, this is what we get. We get the shape of the sampling will be normal, if there's a large enough sample. So the first thing is, if we know that the original population and those original babies are normally distributed, so if we're sampling from a normal group, okay, any size of sample is okay. Like we said last time, it only gets skinnier, it only gets better. If we are sampling from a distribution that is not normal, however it is symmetric, so think uniform or even bimodal, something that is symmetric. Whoops. Not normal, but symmetric. In this case, we generally say, please use an n equal to 30 or more. Okay, sample size of 30 or more. If the sampling distribution, if the sampling that we are looking at from the original data is very skewed, then we need larger samples, maybe 500 or more. Because it would take longer for that central limit theorem to kick into full fruition. So let's talk about one example. Here, then I'm following your class notes here. With this example, we're talking about frogs, and we know that some wildlife scientists have studied a certain species of frogs. And for these frogs, there are some known things. They know that the adult frogs should weigh an average of 118 grams. So I'm going to say the true average for adult frogs is equal to 118 grams for adult frogs. Okay. They also know that the true standard deviation for these frogs is 14 grams. So the first question we have is, if a random sample of 50 adult frogs is taken, and it gives a mean weight, so our X bar is equal to 110 grams, Is this weight, this average for the 50 adult frogs, is this weight unusually low? And so actually looking at this problem initially, you're likely thinking, well, wait a second. 118 is not that far away from 110. But remember our discussion from last class that when you're looking at an average of an entire group, just like if for you all I was looking at the average of an entire class's test scores, for me to move something by 8 points, that's kind of a big deal, right? So for me to say, oh, okay, well, I know the truth for all stat students is a 98 on the test. And then I said, but this group of 30 students just now made a 90. That's much bigger than saying one student. And so the question is, well, maybe it's kind of hard for us to tell by just looking, but the question is that 110 actually too far, or is it still okay with a sample size of 30? The easiest way for us to see this is actually to take a z-score, so let's do that. Remember from the last screen we said that z is equal to x bar, subtract mu, divided by the original standard deviation over the square root of n. In other words, we found a 110, we are subtracting a 118, and we are dividing by that standard deviation over the square root of n, which is 50. Okay, let's calculate this. So 110, subtract 118, divided by, and then I'm putting in 14 over the square root of 50. Okay, here I see that we have, wait a second, there's no way. I need to put parentheses on top of this fraction. Be sure you do that when you're calculating also. Okay, second insert parenthesis, second insert parenthesis. Okay, I'm getting a z-score of negative 4.04 if I round to 2 decimal places. Remember with z-scores, because that's been normalized, it's been standardized with the original data, we have values that are centered at 0, and where if we go beyond plus or minus 2 standard deviations above or below, we consider something unusual, and beyond 3 we consider it very unusual. So 4 steps, 4 standard deviations below what is typical is huge. This means either the sample actually was biased and we have just a sick group of frogs, but hopefully if it's a random sample, it's actually not biased. So it could have meant that if the sample was bad or corrupted somehow, or it could mean that actually the truth that scientists believed, that it's now in question. Maybe they were wrong. Because if that's in fact the truth, it is very unlikely that we would get a value this low. I mean, even without me pulling up StatCrunch, if you remember the basic empirical rule, yep, that's a 3. Then you remember that it was already very unlikely to be beyond a positive or a negative 3. Let's see what that was. That was 1 subtract 0.997 divided by 2. Just here, even without going out that one more step, it was already that low. It was already less than even 0.1% likelihood on that left-hand side. And remember the way I did that is I used empirical, the 99.7, subtracted it from 100%, and then I shared it to both tails by dividing it by 2. It's very unlikely, assuming the 118 is the truth, that we would have gotten an average weight of 110. Now on a lot of your problems that you're practicing, you may not choose to z-score. You probably won't choose to z-score. In fact, you'll probably use original values and go to that normal calculator like I demonstrated last class, or go use the Excel sheet that I've pulled up with you before, and simply plug in the values, right? So what I'm saying is, as long as you know what standard deviation to use and what average to use, you have technology to pretty much do all of the heavy lifting for you. So for the second question, what percent of similar samples would have average weights less than 112? So similar meaning random. And since we are not hypothesis testing yet, we have not officially thrown out the 118, so we will assume it to still be the truth. We'll have an average weights less than 112. And so again, the biggest thing that you need to be able to tell the computer when you go into StatCrunch, let me just show that you're at the normal calculator now, right? You're in StatCrunch. The biggest thing that you need to be able to do is on the computer, you need to be able to say, what is the mean? What is the standard deviation? And then most of you are pretty good at going down here and choosing the correct sign, whether it's less than, equal, or greater than, equal, whatever it is, and putting in the value to get the percent that you need. This is in StatCrunch. Excel is also quite similar. You just have to use the matching pictures. So when I'm reading this, well, the mean is easy, right? The mean doesn't change. It doesn't matter if you're looking at individual frogs or average frogs. The mean, we are saying, if this is the truth, 118, then that's the truth. That's what you should get, okay? That will always be what you put in, 118. Now, for standard deviation in your homework, sometimes you will be tricked. Sometimes it may be appropriate to use the original 14 grams. Other times it is appropriate to use this value down here, the 14 divided by square root of 50. So the biggest difficulty for you is deciding which one is appropriate. Let me show you something. Look here in the words for part 2. What percents of similar samples would have average weights less than 112? I am not saying what percents of similar samples have weights less than 112. I am saying have average weights less than 112. When you see this, average, I'm looking at the average of this being less than something. When you're finding a probability, this right here is your sign of, uh-oh, we're talking X bar. We are thinking averages. We are using central limit theorem. We are using standard deviation modified. So once you type in 14 divided by square root of 50, let's see what that is. Standard deviation here is, I'm getting about a 1.99. You type that into StatCrunch, and you may find that you want to go more decimal places. A lot of times people will actually go even 5 decimals so that rounding doesn't mess up. Let's do this. So maybe I would go, say 1.979899, like that. Just because that way the technology is matching closer to what the table would have had if I were doing things the archaic way we've discussed. So once you do this, well, okay, now you're going to go on here and say, okay, well, and I'm looking for less than or equal to 12. And you'll get some value. And of course I can change this question for between, more than, just like last time, 5th percentile, which is putting that inequality to the left and using a percent up under the curve, where, you know, percentiles, you're out here putting in the information, and getting the question mark would be the value, that's the mark off on the outside. But the idea, again, is just knowing if you are updating your standard deviation or not. And the key word is average. You will have problems that try to trick you. And they will say, what's the probability of an individual frog being less than 112? Try that yourself. Try finding the probability of an individual frog being less than 112 using 14 grams, and you will notice that it's actually quite likely, because individuals can jump around much more than an average for an entire group.